Let's do exploration 2, which reads, assume that e to the x, cosine x, and sine x equal their Maclaurin series for complex numbers as well as for real numbers. And in part 1, we're supposed to find the Maclaurin series for e to the ix. So let's begin by reminding ourselves what the Maclaurin series is going to be for e to the x. And that's going to be 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and that's going to continue. And so if what we want to find is e to the ix, we're just going to do what we've done many times over, which is to substitute in ix every time we see an x. So I'm going to have 1 plus ix plus ix squared over 2 factorial plus ix cubed over 3 factorial plus ix to the 4th over 4 factorial. And then we want to evaluate these I squareds and I cubes and I to the 4ths, and that's why in the reading just above exploration 2, you were supposed to remind yourselves what the power of i's were. So we're going to have 1 plus ix. I squared is going to give us a negative sign, so we're going to have negative x squared over 2 factorial. I cubed is going to give us a negative I times x cubed over 3 factorial. And I to the 4th is going to give us positive 1. So we're going to have plus x to the 4th over 4 factorial. And that will continue out, but this gives us the basic pattern. So part 2 says, use the result of part 1 and the Maclaurin series for cosine x and sine x to prove that e to the ix is equal to cosine x plus I sine x. Now, I think prove is a little strong. We're just going to show that that's what this is. And we're just going to begin by writing down the Maclaurin series for cosine x, which gives us 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and that continues. And if you notice, this is equal to the real parts of e to the ix. And then the second thing we're going to do is we're going to do I sine x, and we're just going to distribute that I across all of the terms for the Maclaurin series of sine x. So this is going to give us ix minus I x cubed over 3 factorial, and the series continues. And if you notice, that's equal to the imaginary terms of e to the ix. So if we add these two series together, we're going to get all of the pieces. So we do indeed have e to the ix is going to be equal to cosine x plus I sine x. And then we can move on to part 3, which says use Euler's formula to prove that e to the I pi plus 1 is equal to 0. So let's give ourselves a little more room here. And we want to show that e to the I pi plus 1 is equal to 0. Well, we're going to use Euler's formula, which is sitting right here, and use that to expand e to the I pi. And so we can write it as cosine pi plus I sine pi plus 1. And the cosine of pi is going to be -1. The sine of pi is going to be 0, and I'm going to have plus 1, and that's going to be equal to 0, which is what I was supposed to show. Now, I wanted to bring one more thing to your attention, which is that Euler's formula is really your key to never having to remember another trig identity. So, for instance, maybe you don't remember what the formula is for sine 2x. This happens to be one of the only ones I remember, and I know that it is 2 sine x cosine x, but we can show this. So we've got e to the I 2x, and this has to be equal to the cosine of 2x plus I times the sine of 2x. But that's not the only way I can write this. I can also write this as e to the ix times e to the ix. And then I'm going to use Euler's formula for each part. So I'm going to have cosine x plus I sine x times cosine x plus I sine x. And I'm going to do out the math, which is going to give me cosine squared x plus I times 2 cosine x sine x minus, because I'm going to have I sine x times I sine x, so that's going to give me I squared and a -1 sine squared x. Now that has to be equal to my expression from up here, which is cosine 2x plus I sine 2x. And you know that the real parts have to be equal to the real parts. So if I say the real parts of the left-hand side have to be equal to the real parts of the right-hand side, then I'm going to have cosine squared x minus sine squared x is going to be equal to cosine 2x, one of those that I can never remember. And I can also say that the imaginary parts of each side have to be equal. So that tells me that cosine 2x sine x has to be equal to the imaginary part of the right-hand side, which is equal to sine 2x.